आफ्टरनून।
कैमरे की वजह से भी जो लाइट से जो ऐसा होगा।
अभी आवाज आ रही है?
मेरी श्रुति, मेरी आवाज कैसी आ रही है?
आ रही है।
हाँ हाँ ऑफिस ऑफिस। हाँ
Good afternoon, sir.
Hello, good afternoon.
Hello, sir. I'm Brahmata Mahapatra, the event head of this summer school. So,
Uh, Nice to meet you.
thank you for accepting our invitation in such short notice, sir. We are really grateful for that. Actually,
No problem.
uh,
I'm very happy to present this work.
yes, sir. So, just because we have some time, like 8 minutes before we start the event, so. Uh, I'm just letting you know. Actually, right now a startup expo and our means IIT Institute experimental research expo is also going on simultaneously. So the offline participants are there. And yesterday also we had this event in offline mode. So there were various talks and lab visits and all that. So today you and Jagdish are two of the uh, highest researcher in your field, sir. So we are really honored to have you. And
Thank you
we
so
will
much.
just wait a bit and then we'll start the event, sir. So thank you, sir, for accepting.
Thank you. Thank you.
Uh, Sir, one more thing I forgot to ask. So can we record this session?
Yes. Are you gonna post it in YouTube or any place? Because I want to put my talk in YouTube. However, I think the one I want to post is it will be like 1 hour, and this is like 40 minutes. So I think yeah, I think just to try that there is no overlap. So my question is, are you gonna post it in YouTube or
Uh,
somewhere else?
yes, sir. Actually, this event is being live streamed on YouTube. So it
Okay.
will be in that form.
Okay. Okay.
Yes, sir. So maybe we can also record and post this as a separate video because the entire event is being live streamed. So we will clip your talk out and then post it as a separate video as well.
Mhm. Okay.
So yes, sir.
Good morning, Professor Lamza. I'm Shruti Kurki. I will be the host of this event today. So it was great to have you in this event.
Thank you. Thank you very much.
And shortly we will start the event once the participants join.
Perfect.
Thank you, sir. Thank you for your patience.
Thank you.
Good afternoon to all dignitaries and participants. With warm regards, I welcome you all to day 2 of IEEE Summer School on Nanotechnology. Nanotechnology revolution has many beneficial effects in almost every aspect of our daily lives. One of the famous computer scientists and mathematician, Ralph Markell, said, nanotechnology is an idea that most people simply didn't believe. Nanotechnology let us build computers that are incredibly powerful. We will have more power in the volume of sugar cube than exists in the entire world today. Understanding the power of nanotechnology in today's world in our IEEE Nanotechnology Student Branch Chapter, IIT Indore has organized a 3-day program titled IEEE Summer School on Nanotechnology, and the theme is Artificial Intelligence and Internet of Things in Nanotechnology towards Digital Agriculture. This is a 3-day hybrid program with successful conduction of inaugural ceremony, plenary talks, and industrial talks with lab visits and SIC visit. We are proceeding with the day 2 of IEEE Summer School on Nanotechnology. we have organized a startup expo in the campus of IIT Indore, which is being conducted. Next, we have plenary talks online. Today, we have two renowned and distinguished speakers, Professor Mario Lanza and Professor Chenupati Jagdish. So, with this brief about the event, let us proceed with our first plenary talk. I would like to welcome Professor Mario Lanza, Associate Professor at King Abdullah University of Science and Technology, Saudi Arabia. Professor Mario Lanza got PhD in Electronic Engineering with honors in 2010 at Autonomous University of Barcelona. In 2010-11, he was a NSFC postdoctoral fellow at Peking University, and in 2012-13, he was Marie Curie postdoctoral fellow at Stanford University. In October 2013, he joined Suzhou University as associate professor, and in March 2017, he was promoted as school professor. Since October 2020, uh, he is an associate professor of materials science and engineering at King Abdullah University of Science and Technology in Saudi Arabia, where he leads a group formed by 10 PhD students and postdocs. His research focuses on how to improve electronic devices and circuits in 2D using 2D materials, with special emphasis on resistive switching applications. Professor Lanza has published over 185 research articles, including one Nature, two Science, and six Nature Electronics, and multiple IEDM proceedings, among others, and has registered four patents, one of them granted with 1 million USD. Professor Lanza has received multiple top distinctions like IEEE Fellow, Young Thousand Talent, Marie Curie, among others, and he is a distinguished lecturer from the IEEE Electron Device Society. Professor Lanza is editor-in-chief of the journal Microelectronic Engineering elsewhere, and he serves as the board of many other journals and international conferences, including IEEE IEDM and IEEE IRPS. With this brief introduction, I welcome you, sir, and now you can proceed with your talk. I would suggest participants to ask their queries in the end of the talk, that is in Q&A session. Thank you.
Thank you very much for the nice introduction and for inviting me to do this presentation. So I would like to ask you, can you see my screen now?
Yes, sir, we can see your screen.
Okay, fantastic. So I'm going to start my presentation. I'm going to talk about hybrid 2D CMOS microchips, which is a quite exciting topic recently. And this is the outline that I will follow for my presentation. And I will start to make an introduction on 2D materials and why we should put them in silicon microchips. So here in this slide, you can see the structure of a two-dimensional layer material. This is cross-sectional view, and this is the top view of a monolayer, and this is the top view of a bilayer. These materials have covalent bonding in plane and van der Waals bonding out of plane. And this gives them quite unique properties such as giant electron mobility, high thermal conductivity, excellent mechanical properties, is very strong. And this is very interesting for optoelectronic applications. They are transparent when they are very thin. And we have 2D materials with different band gaps. So we have materials that are conductive, like graphene, semiconducting, like molybdenum disulfide, and a little bit more insulating, like hexagonal boron nitride. This hexagonal boron nitride is the material that I use for my work, as I will show you later. But the first question that we need to ask ourselves is, for what can these 2D materials be useful within the structure of a modern microchip. So here you see the cross-sectional view of a modern microchip. This is an Intel. It has, you know that this is modern because it has this characteristic back power delivery scheme. The energy supply vias are in the back. This very, very small part is the only part that is in fact semiconducting. And here you have the routing wires, which are basically conductive material and insulating material. So here we have to think where to put the two-dimensional material. First of all, I would like to say that these two-dimensional materials can be produced by different methods, but the most promising method is chemical vapor deposition, and that requires high temperatures above 900 degrees. Okay, so if you have this situation, you cannot grow the material directly on a sample or on a microchip that has been previously processed. So because you will destroy the whole things that have been processed there. So basically what one approach that many people use is to start from an empty wafer and grow a two-dimensional material there. Okay, using this approach, the main concept idea that has been used is to use the two-dimensional semiconducting material to replace silicon to make transistors. So silicon transistors, here you can see the cross-sectional view of the transistor and detail of the channel region where you can see the silicon atoms. So this thing has been the flagship device for modern electronics. You can grow the silicon without defects. You can have a good interface with dielectric. However, when you make the transistors very small, performance is degraded due to leakage current towards the substrate, horizontal phonon scattering here, and short channel effects. And the idea is that if we have an ultra thin semiconductor, we will be able to have a better electrostatic control over the channel. However, this idea, and here you see a prototype device from IMEC. However, this idea that sounds so nice, when you go to try it in a real device, it is not so easy because the two-dimensional material, in fact, grown by this method, it has several lattice distortion and impurities. You know, the material can also have pinholes. It can also have some contaminants if your device is used for, requires transferring the two-dimensional material from another growth substrate to your target wafer. But this is not the case here. Anyway, metal evaporation produces damage. There is high source and drain contact resistance in the transistors and bad interface with the gate dielectric. Nevertheless, several studies have fabricated transistors, but very few studies analyze small transistors with small channel length statistically. This is one of the few in which the authors from IMEC report that when you go very, very small, the properties of the devices degrade. There is high variability, and this figure of merit called subthreshold swing increases a lot, which is bad. You always have a kind of hero device, which is what unfortunately several professors show in their papers, but you need to do things statistically, and this statistically going to small degrades the properties. And this not only happens for the subthreshold swing, but this also happens for the threshold voltage and for the currents driven by the devices, as you can see in this ACS nano paper done by my former student when she went to IE. Moreover, that is only what we call the time zero variability. However, if you start to test the device for many, many cycles, many other problems can appear in terms of yield, reliability, variability, and stability. If you are more interested in this topic about reliability of 2D materials-based transistors, you can check this excellent paper from the group of Professor Tibor Grasser. But for you, to show you something more graphical, you can see here one comparison. This is what happened in a commercial graphene field effect transistor backgated with aluminum oxide gate dielectric. You see that as we make the same measurement for 2000 times, the shape changes, the minimum point changes, the height of this point changes, which changes the on-off ratio. So basically, this is what nobody shows you in the papers, but in fact affects. We have managed to improve it a little bit in the transistors, and in our 2D materials based membristors, you can see that we measure many cycles, and the on off uh, ratio changes. So, the on-off ratio does not change at all in these membristors. So this is something we need to analyze. We need to get used to analyze things statistically and over many cycles. So another approach to integrate 2D materials in the microchips is to get a pre-processed microchip and transfer the 2D material on top. So we grow the 2D material on an independent substrate at high temperature, and then we use a room temperature process to transfer the 2D material on top. This is done using a polymer medium. So here you can see the first two examples. This is from the company IBM. They fabricate a circuit on silicon containing 4 inductances, 3 transistors, 2 resistors, and 2 capacitors. But the transistors are only the source and drain, and in fact, the channel is missing. So basically, they transfer the graphene on top, they finish some contacts, and then they measure. So the size of the channel of the transistor here is 10.8 micrometers square, and the authors observed that the circuit with graphene channel in the transistor shows a cutoff frequency 10 times higher than the circuit with silicon transistors, which is quite interesting. In this other article, the authors use the graphene as conductive paths in a circuit that is a camera. So they use a CMOS readout circuit and they transfer the CVD graphene on top. The graphene channel conductive path, let's say, occupies an area of 100 micrometers square. So both of them are low integration density. We also find some companies, one from the European 2D pilot line, that can help you to fabricate your transistors. You can design them, and they help you to fabricate. However, the minimum feature size is 5 micrometer. So this is all also low integration density. And this is a recent study in which they have a CMOS circuit, and they put this graphene layer on top, which covers an area of 1,296 micrometers square, and this is used as a biosensor. So this is also low integration density. So for these approaches, it is necessary to transfer the 2D material, and this can be problematic. However, I have to say that IMEC has made big progress in this. They have wafer scale transfer of monolayers using wafer debonding techniques. It's not the typical process that we use in the universities, but they observe that for monolayers, they have quite a nice performance at the transistor level, although they need to improve it. I also want to say that I have done several tests in my lab with another method, of course, and we observed that multi-layer 2D materials don't crack so easily and don't form so many wrinkles. So this is something interesting, indicating that the transfer of 2D materials that are multi-layer, which is the one I use in my devices, may be a little bit easier. There is another approach that has been recently published by a group in MIT, in which they have a CVD system with 2 heating zones, and they put a CMOS processor wafer inside the heating system. However, they put it in a low temperature zone that is 250 degrees. So basically, they have the CMOS wafer and they grow the material on top of the wafer, but the material pass one zone that is heated at 1000 degrees, so there is the chemical reactions necessary, but then it's deposited on the wafer, which is in the 250 zone. In this way, you don't damage the surface of you don't damage the CMOS wafer, and you can grow your circuit on top. And the authors fabricate one hybrid 2D CMOS SRAM cell with 2D materials-based transistors and 4 CMOS transistors. This is a good proof of concept demonstration. However, the transistors that they use are huge. This is like around 68 micrometers square. And the currents that they observe is 1,000 times lower than the best one demonstrated for this material. So there's still a very long way to go, but this is an interesting approach because it avoids the transfer. So in my laboratory, what we do is we work not with transistors, but with memristors. The transistor is a device in which the current flows homogeneously across along the whole channel. So if you have some defects in the in the channel, or like a wrinkle or something, this will affect a lot the characteristics of the device, especially if the device is very small. In our case, we use memristors. This is a metal insulator metal structure. When we apply a electrical stress between the electrodes, we can trigger the dielectric breakdown. We form one conductive filament across the insulator. And when we switch the reverse uh, polarity, we can partially break this filament and trigger a high resistive state. So we are, by changing the polarity, we can switch between this low resistive state and high resistive state. The good point is that this current flows locally only across the filament. So if we have a top view, it will be like this. So if you have here wrinkles, rest of polymers from the transfer, etc., it will not affect so much the conductance of the device. Moreover, there is a second interesting point, which is that the resistive switching phenomenon takes place in materials in which the bonding is not very strong. That means that the materials have a lot of local defects. The material that is normally used for this kind of devices is hafnium dioxide, and you can see that this material has a lot of defects. So if we have a two-dimensional layer material that is not perfect, that contains some defects, it's not a problem. In fact, the defects are necessary for the correct functioning of the resistive switching device. So if you apply these electrical stresses over many cycles, you can switch the resistance of the memristor, as in the video that I have shown you. Here you see that there is a higher variability. This is in a metal oxide. But when you should do this for thousands of cycles, you can see that the device reaches a permanent low resistive state. It means that the filament that you have created is too wide and it cannot be partially broken anymore. So what is the idea from our group is to use two-dimensional materials grown by chemical vapor deposition that contain some intrinsic native defects, because the two-dimensional material is very stable. You need a lot of energy to produce defects in the two-dimensional material. However, in these local defects, atomic movement takes place at lower energies, and therefore here we can form the conductive filament. And here is the clue: the conductive filament will be surrounded by stable material, and therefore it will be confined. That's the word that I think is the clue. There is a confinement effect in the out of plane current, and this may lead us to a higher endurance. That's the concept idea. So first, let me show you about our work on hexagonal boron nitride based membristors. And as all other authors, we do it on silicon oxide substrates. So this is the boron nitride that we use. It is grown on copper. This is the optical microscope picture. This is the SEM picture. You see the surface of the copper is rough. This is the AFM picture. And you can see here that the surface of the copper is rough. And here we have the boron nitride multilayer on top. And as you can see, it contains several native defects. However, when we scan the surface of this sample with a conductive AFM, applying 0 volts, so basically very, very small voltage, we observe no current. And you will say, yeah, of course, because you are not applying voltage. I have to say that applying 0 volts in the CAFM is a good method to detect pinholes in two-dimensional materials, because the all the CAFMs have a very small offset, and when you scan metallic tip with metallic substrate, there is current even if you don't apply voltage because of this small offset. Okay, so the fact that this picture does not show any current spot, it means that this is insulating and it has no pinholes, even if it has so many defects. These defects are not related to the focus ion beam used to collect the TM image, because as you can see, when we do this test in exfoliated material, we don't see such a large amount of defects. In fact, the image is perfect. We also analyze the same picture that you see here, but now applying some voltage. And what we observe is a very inhomogeneous current distribution with some hot spots and some areas that are insulated. And actually, this is the clear characteristic of um, uh, this is a clear signature of materials that show resistive switching. This image is very similar to that you observe when you measure hafnium dioxide. So when we saw this, we thought maybe this material can show non-volatile bipolar resistive switching, and then we fabricate our devices. We deposit the top electrode by photolithography. We transfer the 2D material. We deposit the top electrode doing another photolithography, and finally we remove the boron nitride that is on the bottom electrode. So you can see here there is a slight color change, and here it is even peeling. This is because we need to make a good contact with the bottom electrode to the top electrode. And here is the cross point device, which you can see better in this SEM picture. This is the bottom electrode, top electrode, and the wrinkles, which is showing that this is a continuous wave. Okay, so in this device, we measure many devices, and we show here, this is the typical characteristic for many devices. Each line is one device. Initially, the currents show high variability. The breakdown voltage show high variability. When we apply a current limitation of 1 milliamp, we observe that we have triggered the low resistive state. And then when we apply a negative voltage here you can see that the current reduces, so we trigger the high resistive state. And in the next cycle, the sample now, it triggers the dielectric breakdown at around 2.5 volts. And actually, we can do this cyclically for many times. And in fact, we have reached endurances of up to 1000 cycles. And the most important thing is that when we fabricate many devices with this 25 micrometer square gold multi-layer hexagonal boron nitride grown by CVD method and gold, we observe that most of the devices show very similar performance and low variability. Actually, it's very similar to the variability we observe in hafnium dioxide. So this was the first surprising thing, that this thing can be so consistent, and actually the good reproducibility and high yield when using multi-layer. When using monolayer is not good yield because we get many cracks, but for this high yield and low variability is what makes this study qualify for publication in Nature Electronics back in 2020. The switching mechanism is related to the penetration of metal particles into the layer boron nitride. You can see it here, and actually we can see it also by measuring the gold signal in samples that have been stressed. It's quite obvious that there is gold penetration. But actually, when we fabricate devices with different top electrodes, we observe different speeds for dielectric breakdown formation, which is related to the different diffusivities of the metal into the boron nitride. So basically, this is indicating again that there is metal penetration into the boron nitride. So until here, we were very happy. Everything was quite well, and we published a nice paper. But then we tried to do the devices smaller. So we use electron beam lithography to fabricate 320 by 420 nanometer devices. And also we tried to make larger crossbar arrays. And when we test this type of devices, we observe something interesting, which is we get randomly around 50% of the devices that show a characteristic like this. They show that the electric breakdown, we use a current limitation like before, like for the big devices. However, when we apply the negative ramp, this device shows much higher current than the current limitation, and it does not trigger the reset. It just stays in permanent low resistive state, which means that the device has failed. So this is a phenomenon called overshoot, and when it takes place, all the devices are broken. And this phenomenon takes place randomly in 50% of the devices. The other 50% shows something like this. There is no current overshoot. The current during the negative ramp is similar to the current used as current limitation. And when that happens, the device reset, always. However, in the next cycle, the overshoot may happen. So basically, these devices show an endurance very poor of around 5 or 6 cycles. So basically, the conclusion is that when we make the devices small, this does not work because the presence of current overshoot. And we managed to publish a paper explaining all this phenomenon, but in fact, these were very bad news for us, and we were quite disappointed. So we think how to solve this problem. And then we realized that most professors in the universities, They test the devices on silicon oxide using these test structures. However, the companies don't do it like this. The companies use a microchip, and they have these CMOS transistors, and they integrate the resistor switching material, in this case is hafnium dioxide, on top of the via of the transistor. So basically, you have one transistor in series with one memristor. And the transistor is very useful because the transistor can be used as current limitation. When you put a gate voltage, there is a maximum drain current this transistor can be give and not more, no matter what happened to the resistor switching material. So this is a very interesting point. Actually, moreover, the transistor can also be used as selector in the crossbar array to avoid sneak path current. So with this concept idea, we fabricate a CMOS wafer in a commercial foundry, and we finish the wafer at the last metallization layer. The surface is like this. Okay, we don't finish the wafer using passivation, etc. Each wafer contains 50 microchips. We cut them. It's 2 by 2. This is a 200 millimeter wafer. And then we have several things. This is a multi-project wafer tape out. But here you have this area that contains three elements of interest. One is bottom electrode and top pad for fabricating a memristor. The same, but within a transistor, and the same, but with a crossbar array of 5 by 5 transistors. And then what you can see here is that we integrate we transfer the boron nitride, and we deposit the top electrode. You can see top electrode here, here, and these wires that were not here before, you can see, okay? So we have the continuous boron nitride film, as you can see by these wrinkles, integrated at the top of this transistor. And this architecture has also one advantage, which is the diameter of this metallic via is only 260 nanometers. So the size of this memristor is at most 0.053 micrometers squared. So you see here, my group did not invent 2D CMOS microchips, but my group invented the first high integration density 2D CMOS microchip, which is this prototype. And then here are a few details more about the fabrication, because when you get the unfinished wafers from the foundry, they are covered by silicon oxide, native oxide. So you need to etch it to expose the vias, and then transfer the 2D material, put the top electrodes, and then you have the CMOS transistor, and here you have your HVN memristor. And then we do the electrical characterization. We apply sequences of ramp voltage stresses with different polarities to the device without the transistor, and we just observe erratic behavior, nothing consistent. Because the switching is not really controllable because we don't have the transistor. When we increase the voltage, the device simply fuses by thermal heat because the current is not being limited. The CMOS transistor, on the other hand, works as expected. There is no secret on CMOS transistor. And then here comes the interesting thing. We measure the one transistor, one memristor cell, applying gate voltage of 1.1 volts. And we observe the first cycle is the blue line. It shows that in the backward ramp, there is much more current than in the forward. So basically, we have changed the resistance. And then in the backward, in the reverse IV curve, we see that there is a current decrease. And in the next cycles, they come here. There is no an evident, I mean, the currents are a little bit higher than in the first ramp, but there is not evident a forming process. There is no sharp set transition, and there is no sharp reset transition, and the resistances of the states are very big. So basically, this is indicating that we are not working in a filamentary regime, but we are just slightly changing the structure of the boron nitride, but without really forming a very strong filament. This behavior is reproducible over many devices. In some of them, it's more beautiful. In some of them, it's more ugly, but this is irrelevant. The only thing that matters is how the device behaves under pulse voltage stresses, which is the type of stress used in real devices. So we apply the test when using three different top electrodes. This is titanium, this is gold, this is silver. And you can see that for all of them, we can see that the read when the device is fresh show low current, the read after the write is shows high current. So here what you see is read, write, read, erase, read, write, read, erase. Okay, and you see that for each pair of reads we see high resistance state, low resistance state. So low current, high current, low current, high current. So this demonstrates the presence of non-volatile bipolar resistive switching. By using silver electrodes, we achieve a switching at lower voltages, which is always better for on-chip integration. And we achieve quite decent switching times and switching energy, although they are not world record. They just work well, but it's not super top. What is really surprising is the endurance. The endurance of these cells are 0.053 micrometers squared. They are very small. And at the same time, they show very high endurances with the possibility of tuning this on-off window. Okay, so if you now analyze how many articles in the literature show high endurance, you will find many. But if you analyze how many show high endurance in small devices, you will find only 5, and 3 of them are from companies. Actually, reaching this high endurance in the small devices is very difficult because the energy that you need to give to the device to trigger the switching is much higher in smaller devices due to the presence of less amounts of native defects, and that increases the energy to breakdown and makes everything more uncontrollable. But here we managed to control it very well in the boron nitride thanks to its layer structure and to the series transistor. Just to give you one example, commercial metal oxide memories from Fujitsu show an endurance of 500,000 cycles, not more. And the phase change memories from Intel and Micron show 10 million cycles. So you can see that it is in the same range. Of course, right now we need to make many more tests to observe how is the endurance in other devices. These devices also show one very interesting property, which is if I reduce the gate voltage of the transistor, I also see threshold type resistive switching, and I also can observe a spike time independent plasticity, which is very interesting. These two characteristics can be exploited to fabricate spiky neural networks. So in our article, we did a simulation of a spiky neural network, and we observed that it obtains a quite nice accuracy around 90%, which in the domain of spiky neural networks is significantly high because these networks have normally lower accuracy but very small energy consumption because you don't have a DC bias, you just have these spikes. Actually, in our article, we not only presented the Python simulation, but also the SPICE simulation, which is very important because you always need to make sure that the device, that you can have a circuital structure that can replicate the model of the synapse and the model of the neuron. So
Exactly, sir.
finally, we also, yeah,
We have 10 minutes left for the talk.
yeah, yeah. I have. Actually, we are arriving to the last part of my talk. In the next step, we have also do some in-memory computation, very simple, taking advantage the internal connections of our microchip. So we fabricated some logic gates, although we are now designing a new microchip with different internal connections to be able to make better and more ambitious in-memory computation. And actually, we have also started to do vector matrix multiplication, which is a flagship operation necessary in artificial neural networks. However, so far we have done it only on silicon dioxide using 25 micrometers square gold boron nitride gold devices. And we input some patterns in the crossbar array. And what we observe is that when we use the whole crossbar array, which is 32 by 32, so this is 1 kilobit, we observe that there are some sneak path currents and it's difficult to make it work. However, we find a portion with 16 by 8 that it works quite well. And then we input these 16 digit patterns in the inputs and we measure the current of each column and we observe that we can do the hardware vector matrix multiplication with our crossbar, and the values that we observe are very similar to the software ones. And actually, we compare the error, and the error is a systematic error. It is basically related to noise at low currents, and these points that you see here are related to the different current ranges in our characterization board. So this is something that encourages us to keep, and now we are doing this on the chip using the series transistor. And for these devices, we can also potentiate the resistance of the devices. Uh, let's say in an analog way. So this is something that allows us to achieve different uh, resistance levels, although the on-off ratio for these devices is a little bit low when we use the analog regime. And then finally, we are designing new chips. As I mentioned, this is a picture of our new microchips that we have designed. This is the layout, and this is one optical microscope picture of one of the parts of the microchip. You can see here our microchip contains many types of circuits. It is a true random number generator circuit that is based on one memristor. These are crossbar arrays of memristors. So I think we are trying different applications for the true random number generator. In fact, we have already confirmed the correct functioning using a commercial microcontroller, one Arduino, and then we connect the random telegraph noise signal that we measure to the Arduino, and we can generate a random output of zeros and ones, which is used as unique code like those that you use when you buy things online. And finally, we are trying to do this directly now on the chip, integrating the bond writer on top. But however, I want to emphasize the main challenge that we are having, which is the variability of the hexagonal boron nitride from one wafer to another wafer. So we buy many commercially available multi-layer hexagonal boron nitride. However, there is very big difference on the quality from one sample to another. And what we observe when we open the box and analyze is that this is completely different to the specifications of the manufacturer. So I think suppliers have to improve a lot. Luckily, we are now getting premium samples from the company Extron, which is a company that fabricates MOCVD systems to grow this. And now they give us wafers that are all identical. So we expect to make a much better optimization. So as a conclusion, I will say that the CVD ground 2D materials contain too many defects, and they hinder the performance of several devices like transistors. However, CVD ground multilayer HBN can be used uh, to fabricate memristors and can be integrated on CMOS microchips. And I really encourage everyone to try to integrate the 2D materials on CMOS wafers, because as you can see, the performance can be very different than on silicon dioxide samples. If you are more interested in our work, you can check our recent articles. And finally, I would like to thank all the students of my group here in KAUST for their hard work and dedication to this project. And that's everything from my side. I will be happy to answer any question. Thank you very much.
Thank you. Thank you so much, sir. We would request participants, if you have any doubt, then please switch on your video and unmute yourself and ask your doubts.
May I ask questions, Shruti?
Yes, sir, you can ask.
Yeah, thank you. Mario, as usual, excellent talk. I hope you are doing fantastic over there and hope we'll be able to meet soon. You're coming for EDTM conference, right?
For EDTO conference this year, I cannot travel to India. I was in the previous conference that was done in Bangalore, and I was very impressed. So I think for this conference I will not be able to come. However, I
Okay.
hope I can make a long trip to India and visit several IIT and IIS.
Okay. So in another avenue, we have another conference in the month of May. Again, it is called
Mhm.
WDC, in a workshop for devices and circuits. So
Uh,
you know Yogesh Chauhan. So he's chairing
yeah.
this. So every year we used to plan these devices and circuits of the entire, national forum as well as international forum. We meet. So this time we are
Mm.
meeting in the beautiful state of Jammu and Kashmir. So
Aha,
I would
that's a nice
share with
place.
you. I'd share with you the information. We are making the brochure currently. So if
Thank
you happen to be free that time during second week of May this year, then you can have another opportunity to come to that conference, because that will be in another state, not only in Bangalore.
Aha. Okay, then I have the opportunity to discover or more places.
Yes, yes, yes. And Mario, when you talked about the CMOS chips, like you are making it from Global Foundries or from Leti Foundation or something else.
No, no, they are from a foundry that we work with in China,
Okay,
and it is very convenient because it is very flexible. You know,
okay.
um, for for a bad driver, you don't want to give a good car. Let's say it in that you want a flexible car. You want a car that you
Yes,
can change many things, etc., and that is also affordable. So this
absolutely.
this foundry is perfect for us. I have tried also other foundries. We can make some prototypes. We have samples, but this one is ideal and it's very flexible. It allows us to change materials, which is very important because as you see right now, I'm mounting my device on a tungsten
Yes,
via. Ideal thing
yes,
will be to have a platinum electrode with different sizes, and this is
yes,
something that other companies don't allow me to do. But this Chinese company is ideal, so they cannot do the smallest transistors and better transistors in the world. They do
yes,
something very good. The transistors are very reproducible and very good, although they are not the smallest ones. But even if they will do smallest ones you cannot afford. So it's okay. I think this is perfect for academics. I think I'm very happy to pass you the contact if you are interested.
that will be fantastic, because I contacted Global Foundries and Leti Foundation. First of all, they run two different cycles, one for academia, one for industry, you may know. So it is very difficult to put in the cycle, because they every time they say August they starts opening and it gets filled up very soon. But yes, whenever we share the design, they are very reluctant to change about
In
whatever
fact,
they are.
let me mention that I am developing a project aimed to design
हेडफोन नहीं है लेकिन
testing
इसमें बात
vehicles
करते हैं तो
for several material scientists and academics. So these testing vehicles will be designed for us. It will not be following all the
Yes,
specifications from the company and then you have to adapt your design. No, no, it will be a
yes,
perfect chip for people who want to play with new materials because
yes,
that factory already can make it for me. And I can give you several chips for free once I get them. So I will make like 12 200 millimeter wafers, and I will have several chips.
yes. And like we as you know, like we are growing here mostly MOS to WS2 via our APCVD system, and probably I would discuss with you more in private. So we can
Mm.
also want to see the performance of our materials with you, because you have the entire setup with you. So if
Mm.
in future, like I'll discuss with you later on this. But
Yeah,
yes, so that part, because unless and until we do collaborations, the work that we have been doing, it is very, very difficult to do, because everything is not available under the same roof. So that
yeah.
is the
The
problem.
most important thing, in my opinion, is small size. This is why I emphasize very clearly the previous microchips are low integration density. My microchip is the first one to have the 2D material with high integration density. So
Yes,
when you do small, devices behave completely different. You have seen it in the transistors with the slides that I present from IMEC. You have seen it also in my own memristors. So whatever the academics do, if this not small, it is less relevant unless you are doing IoT sensors, etc. But in the field of transistors and memristors, it's necessary. So we want to design these testing vehicles for our colleagues so that they can test their uh, materials, no matter it's organic, it's whatever material, but on the proper testing vehicle.
Absolutely. Okay. Thank you so much, Mario. Hope to see you
Thank
soon.
you.
Yeah.
Thank you.
Any other questions by the participant?
Sir, I have a question. Thickness of the
I think I cannot hear very well. I think you are
Uh,
muted, or at least appears
can you
one
please
icon.
unmute?
I cannot hear. No, I cannot hear.
Animesh, you
Maybe
can
when
use another mic or you can use another
or
system. Your mic is not working.
yeah, it's not
Probably
working, or
Shruti
maybe
can,
type.
yes. Probably Shruti can reciprocate his question.
sir, now I am audible, sir.
And now I can hear.
Sir, actually, I have a question regarding the variability of the devices, sir. Sir, does the thickness of the switching material makes an effect on the variability of?
For yeah, so the resistive switching mechanism is controlled mainly by four things, which is the lateral size of the device, the thickness of the boron nitride, the type of metal that you use, and the density of native defects that the dielectric has. And therefore, these four things can play an important role for the characteristics and also for the variability. Now, for variability, we have two types: the cycle to cycle variability in one device, which is more related to the stochastic nature of the switching mechanism. And the other one is the device to device variability, which is more related to the inhomogeneities in the within one group of devices. So the thickness fluctuation of the boron nitride, I mean, the film is quite stable in thickness. I mean, it has a lot of defects, but the thickness is quite stable. It's around 6 nanometer, between 6 to 8, and okay, this is a significant thickness variation of a percentage above 10%. Okay, however, we see that it's quite stable. I mean, it makes more a difference on the forming process, as you can see in our work,
Yes,
but
sir.
from one device to another, it does not make such a big difference. However, I wanted to emphasize something. People should not get too obsessed, because in my lab it happens. My students get obsessed on how beautiful the IV curves are. The IV curves are irrelevant. The only thing that matters are the pulses. Okay, so as far as your pulses look nice, it is okay. Don't worry about the IV curves. If there is variations on the switching voltage, just focus on the pulses, which is something not many people do, but it's the right thing to do.
Okay, sir. Thank you, sir.
Yeah, thank you.
Hello, uh, hello, sir. I have one question. In slide number 37,
Yeah,
uh, in memory stack crossbar array, we use in a neural network.
yeah.
Yes, sir. Neural network. So, how to identify in memory stack crossbar array? How to de- decide the weight each each memory star in crossbar array when we apply the image like here handwritten digit 2. So how to decide the crossbar array each memory star weight?
Sorry, I couldn't understand the question. Can you repeat, please?
In memory star crossbar array each memory star have, so how to decide each memory star weight, so when we apply any image input,
Yeah,
just like three cross three have a one image, so each pixel have one value, then we
yeah.
apply on memory star crossbar array. So how to decide the input is coming, uh, through the memory star crossbar array. So memory star have no value starting, but just like one image, one is a filter. So memory star crossbar array assume a filter. Then how to decide the weight?
Well, I'm not really sure I fully understood the question, but let me maybe describe a little bit what we did here. So
Yes, sir.
actually, you will see it even more clearly in this other image. So basically, what we have
Yes.
is the pattern. What we have here is a pattern, okay, and we have a pattern that has 16 numbers and then 16 values, okay. So one for each row
Yes.
of the crossbar. So you can see this is the first one, this is the second one, and this is the last one. You see, this is a one, and this is a one because we use this one as an example. Okay, so one, two,
Yes, sir.
three,
These
four,
are
five.
inputs. Okay.
So these are the inputs, and in this case they are binary inputs, so they are only 0 and 1. And in the case that of the other slide 37, it was a grayscale. Okay, here is a grayscale. You have different tones. We do this because of course it's easier with binary for our example here. The what you see here is a simulation. Okay, what you see here is a hardware implementation of this vector matrix multiplication engine. And then what we have is that we input this pattern, and then we measure all the currents of the outputs, and then we check what is the value. And then normally what you do is you have to check for the neural network functioning. You have to check which one is the winner, which one is the highest value. And then what you do is you know the value of your memory stores, you know the value of your voltages. Then you do the same but with software, with just we do it with MATLAB, okay? And then you can compare the values of the two of each column. With hardware we obtain this value, but with software we obtain this. But in fact, if you check which one is the winner, yeah. So in both cases is this one. You see the 6.4. This is the lowest value, and this is the lowest value also. So the values are different, but the winner is the same. That's the key point of this operation. Uh, I'm not sure if this answer your question, but this is how this part of the pixels and the inputs of the memristors work. However, the only difference between 37 and 40 is that in 40 we apply a constant voltage here, which is one. Let's say for one we apply, let's say for example, 1 volt, and for zero, 0 volts. While here, what we have is that for the black, uh, for the black, then
Okay.
we apply no spike. And for one that is a little bit gray, we apply spikes with some frequency. And for one that is completely white, we apply very high frequency of spikes because this is a spike in neural network. So instead of one amplitude for one voltage, what we change is the frequency. We increase the frequency. This also changes the conductance of the membrane.
Okay,
I
sir.
think
Sir, in slide number 40, 40,
Yeah.
sir, when we apply in input 1, the bit memory star have some weight.
Yeah.
Yeah. So when see in one row, the one current is row 1 have one current. So how to decide that each column have different current, that input is exact matching the output.
Okay. So the thing is that the values in the input, you don't decide them. The values in the
Yes.
input are given by the patterns that you want to recognize in your neural network. This is an image collected from a database of images called MNIST that has been rescaled, which is something that is for this example is okay, but in fact, for let's say larger for better examples, it should not be rescaled. But anyway, the point is that this uh, these values are not selected by you. These values are given by the data set that you want to train your network with that data set, so that later the network is able to identify other images similar. This is not, these values that we put here are data sets given, are not selected by us. Is that what
Sir,
you asked?
okay, sir. Sir, can we implement this network in Cadence and LT Spice?
Yes, actually, in this paper, the postdoc in charge of the simulation, he also did the spice model of the neuron and the spice model of the synapse. So yes, the answer is yes.
Okay, sir.
Yes, Mario, actually, the questions of the student arises because many papers, they refer to the uses of neural network work via memory stir. And few people say some circuit design, but nobody says like whether the image classification is actually done through that particular circuit. So it is like discretized manner. One reports the circuit, they say it will do some kind of image processing. Another
Yeah,
say, and they give n number of layers saying that this is the neural network work, but nothing is
yeah,
merged. So it is
yeah.
confusing
This is
whether the circuit is actually doing the work or not.
Yeah, this is called hype, and is the main cancer of science in modern times. People don't make the intermediate part and exaggerate that the memory store is suitable for that without doing the circuit design part, which is the critical part. In our work, we did the measurement of the figures of merit. We did the Python simulation for the neural network, but we also did the SPICE simulation of the circuit. So this is, if you are interested on that, check it. We are going to publish a paper soon in Nature Communications, which is a perspective, co-authored with many experts in the field of neural networks based on memristors. And there is a big part. I mean, that I think you will like that paper because it gives the whole hardware picture of the neural network, and it explains every circuital block, everything, and it criticizes very openly and makes very clear comparisons between which papers do all and which papers do the device and the Python. These papers that are device and Python have no connection. They have to do also the circuit design. So I think this is very important. Unfortunately, still, I would say 95% of the articles that try to do that don't put any spice on the circuit design, and that's a big mistake.
Yeah, thank you so much, Mario. And our next speaker has also joined, Professor Jagdish. Good afternoon from India, Professor Jagdish. Yeah, you're
Just
muted.
okay. Can you hear me?
Yes, yes, we can hear you. We're
Okay,
just
that's fine.
conversing with our previous speaker, Professor Mario. He has
Sure.
also joined from Taos. So
Hi,
yes.
Mario. How are you?
Hello, hello. Nice to see you. I'm looking forward to your talk.
Good. Thank you. Sorry, I missed your talk. It's my dinner time, so I had to have some dinner and then be ready for this
Yeah,
talk.
I guess it must be very late. Yeah, but it's
Yeah.
okay. Thank you. Thank you.
Well, congratulations for your IEEE fellowship again.
Ah, thank you so much. Thank you very much. It was really nice. I think it's very important.
Yes.
Okay, so I
So
think I
Shruti, please
think
start.
probably you
Yes.
want to go ahead
Thank you so much.
with his talk,
Yes.
right?
Okay. Yeah. Sure.
Absolutely.
Okay.
We
Let
Thank
me
you
will,
try
so
to
much,
share
Mario,
this
for your
one.
time.
we, uh, Professor Mario Lanza, this is a request from our side that we will take a photograph, that is screenshot of this screen. So I request all
Ah, okay.
participants to switch on your videos. So yeah, thank you so much.
Please smile so we can take a beautiful photograph. Thank you, everyone. Thank you, Professor Laja.
Thank you. Send it to me later, please. It will be very nice. Thank you.
Definitely, sir.
Okay. So I would like to thank our Professor Professor Mario Lanza, Associate Professor of PAUS. We are grateful for your time and efforts you took to share your experience with our IEEE community. So thank you so much, sir.
Thank you, and thank you very much to you for the invitation, and congratulations for the successful organization.
Yes, thank you so much, sir. So now we move ahead with our second plenary talk. Professor Chelupati Jagdish, President of Australian Academy of Science, the Australian National University, Australia. Professor Jagdish is a distinguished professor and head of Semiconductor Optics Electronics and Nanotechnology Group in Research School of Physics, Australian National University. He has received Australia's highest civilian honor, Champion of the Order Australia, for his contributions to the physics and engineering, in particular nanotechnology. He has received 2023 Pravasi Bharatiya Samman Award, highest award given to overseas Indian by the Government of India from President of India. He is currently serving as President of Australian Academy of Science and in the past served as President of IEEE Photonics Society and IEEE Nanotechnology Council. So I request Professor Jagdish to please start your talk. And it is request to the participant that uh, you can ask your queries in the Q&A session at the end of the talk.
Okay, thanks, Shruti, and for your kind introduction. And so I want to thank Tribal and all the IEEE Nanotechnology Council chapter leadership for inviting me to participate in this summer workshop. And so I think I've noted that it's a winter there in India, but obviously you're trying to think of Australian summer. So thank you for calling it as a summer workshop than a winter workshop. Anyway, thank you. And let me see whether I hope my screen can be. Can you see my screen?
No, sir, not yet.
No, now.
No, sir.
Okay, let me see what. See, the WebEx is I rarely use. Sometimes it shows here, but okay, I don't have the option of sharing here. It doesn't show this. You want me to share the window or the entire screen? Okay, let me see whether it's working.
Sir, you can share the entire
Okay,
screen.
now tell me. Now tell me. Is it? Can you see?
Yes, sir. We can see.
Okay.
Yes, sir.
Okay. In that case, can I start?
Screen mode. Yeah.
Yeah, I've done full screen mode from my end. Okay, this is what happens. I think WebEx has got a problem, and then whenever, unless otherwise, I share probably the full screen, and I'll do one thing. Let me do again. Share entire screen, and can you see it now?
No, sir. The screen is not visible.
I don't know why it does this one to me, and so.
Sir, you can, if the issue persists, you can email your PowerPoint to us and we can share it for you.
No, this is too big, Brahmadatta, for this one. That may be
Okay.
too difficult to really send it now. It's too late, probably. But is it okay if I just share it in a non, sort of presentation mode, and probably you can still see that when if I share the window, I don't know. I see whenever I go to the share entire screen, the share option doesn't show on my end.
Sir,
Okay.
sometimes this problem is resolved like that we do with our electronic instruments also, switching on, switching off, and switching on. So if you can go out and join back, sometimes this problem gets solved. I do not know
Okay.
why.
Okay, that's okay. I can do that one. So looks like that's an engineer's solution to the problem rather
Yes.
than solving the problem, switch on and off, and hopefully it works, right? Okay, I'll come back.
Yes.
Just give me 1 sec then.
Yes.
Yeah. Thank
Yes.
you.
Yes.
Come back, sir.
Can you see it
Uh,
now?
yes, sir. Yes.
Yes, sir.
Okay,
It is proper. It is in full screen mode.
full screen. Oh, that's good. Thank you. So Shaibal, looks like engineer's solution has worked. Good. Thank you. Okay. So I mean, this I think afternoon for you, and I'm going to talk about the. I'm trying to avoid the screen. Okay. Hopefully this is not displaying on your end, and so.
Sir, just kindly excuse my excuse, but I just want to confirm that, sir, we are recording this session. So is
Sure,
it
which is
okay?
fine. Which is fine.
Yes.
Sure.
Yes, sir.
Okay.
Thank you,
Thank
sir.
you. Thank you. Yeah. Okay. So anyway, but so today I'm going to talk about semiconductor nanostructures for optoelectronics applications. And so let me see if I can put this one there. Yeah, okay. It has been mentioned that I am from the Australian National University, and I also have honorary appointments in various parts of the world. And I want to thank all my colleagues for inviting me to be associated with these institutions in India and Japan and China and Taiwan and UK and various parts of the world. So really today's talk is a collaborative effort between my group at the Australian National University and many groups in Australia, US, UK, and China, and Sweden, Italy, Russia, and Switzerland. The beauty of science is that there are no national boundaries and in science, and we can all work together. It's been a pleasure for me to work with all my colleagues in various parts of the world. And also I want to thank the students and postdocs, those who contributed to our research in these groups as well. This is my group at the Australian National University. The picture is a bit old, and these are the people, those are actually doing the work, and I want to thank them for their contributions. And also I want to thank past members of the group as well, because today's talk is really covering a broad spectrum of activities which are happening for more than a decade or so. And I also want to thank my academic colleagues, those are leading various aspects of our research program with the blue, and also academic colleagues, those who moved on to the greener pastures, those are also listed in the green as well as our funding agencies for their support as well. So here is an overview of my talk, and I'll give you motivation for why we want to work on semiconductor nanowires and nanostructures, and how do we grow these structures, and then wide variety of applications. And I'll share with you about using nanowires for lasers and LEDs, terahertz detectors, solar cells, and photoelectrochemical water splitting to generate hydrogen, nanowire sensors, and nanowires for neuron growth, and I'll draw some conclusions. So in terms of the future, the World Economic Forum has identified some of the optical technologies which are needed for the next generation technologies to be developed. Holographic displays in the future will end up having holograms coming out of your phone so that you can be able to interact with people in 3 dimensions. And also that it will be important for the telemedicine and a range of applications, for example. Wearable optical sensors, and they are monitoring your health continuously. And so again, that's becoming very important. And already there are some sensors which are in various Apple Watch or the Samsung Watch and others. But I think we are moving towards a much more high resolution sensors as well. And like navigation and communication, so-called LiDAR for about autonomous vehicles, which can monitor their surroundings. And 3D vision and gesture recognition, and enhanced machine vision and augmented reality. These are all aspirational technologies, require fundamentally new approaches for smart and miniaturized optical systems. And we got a center of excellence called Australian Research Council Center of Excellence on Transformative Meta-Optical Systems, TMOS, which is led by my colleague, Professor Dragomir Neshev. And we also got 5 partners in these various institutions. About 15 chief investigators are involved with many students and postdocs. This is called essentially active meta-optics. So in this center, what we are doing is that we are using nanostructures to generate light, and then using nanostructures to manipulate light, and then also use nanostructures to detect light. If you want to develop any optical systems, you need to have all 3 of them. And we are really developing these miniaturized optical systems for the next generation technologies. So nanowires are seen as building blocks for the next generation electronics and photonics. And one of the unique things of the nanowires is that the lattice mismatches are no longer an issue. Whenever you're making 2-dimensional materials, you always have to worry about what is the lattice constant of the layer which you're really depositing, and what's the lattice constant of the substrate. Lattice constant is the size of the unit cell which repeats itself in a crystal, for example, whether it is silicon crystal or gallium arsenide crystal or indium phosphide crystal, depending whatever the crystal you're talking about, the unit cell size is called lattice constant. So you've got a material which got a large lattice constant with respect to the substrate. It can expand without creating any dislocations in the case of nanowires. But whereas in the case of 2-dimensional materials, if you really have got, they exceed some particular critical thickness, and they relaxes back to the original lattice constant that lead to dislocations. Again, if you've got a smaller lattice constant with respect to the substrate, this can contract without creating any dislocations. So that means, in principle, you should be able to make nanowires of any material on any substrates without the constraints of lattice mismatch, which has been the case when you're dealing with 2-dimensional materials, for example. And so that means, because we have been discussing about, 3-5 semiconductors are mainly used for optoelectronics and also for high-speed electronics. But silicon, of course, is the workhorse for the nanoelectronics and microelectronics also. The challenge has been how to bring these 2 technologies together. Lattice mismatch has been a constraining factor, but with the nanowires, they would not have that limitation. In principle, we should be able to make 3-5 nanowires on silicon, and thereby we'll be able to make high performance, both optoelectronic and electronic devices on silicon. Also, you can make axial heterostructures. These green materials are different than the red material. You can dope these nanowires with the p-type doping and n-type doping so that you can make p-n junctions within the nanowire for making LEDs, lasers, and solar cells, a range of applications. And also you can make radial heterostructures or core shell nanowires. And this red material is different than this pink material. So that means you'll be able to make multi-shell structures, one on top of the other, for example. You can also create a branch nanowires, which opens up opportunities for us to be able to make 3-dimensional architectures. In fact, here are some of the examples from our own laboratory, where we have shown we can grow gallium antimonide on top of gallium arsenide despite large lattice mismatch. And because gallium antimonide is an important material for infrared detector applications, and we have demonstrated they can make atomically perfect gallium antimonide on top of gallium arsenide. You can also make branch nanowires of indium arsenide on top of gallium arsenide, which could be used as cantilevers and scanning probes also. Also, you can create nano trees, which are very good for energy harvesting applications. In this case, I'm showing indium phosphide nanotrees, which are for splitting of water to generate hydrogen, for example. And most recently, we started moving from nanowires to nanomembranes, and I'll come and share with you how we are able to make these structures also. And then once if I demonstrate how do you grow these structures, and then I'll share with you, already there are reports in the literature of wide variety of devices being made using nanowires, LEDs, lasers, photodetectors, biosensors, and solar cells. And then I will share some of our own results in this talk. And most importantly, in IBM research has I recently demonstrated nanowire indium gallium arsenide nanowire transistors on top of silicon, because of the fact that International Technology Roadmap for Semiconductors have identified nanowires are going to play an important role in electronics as well. If the nanowires are so much of importance, how do you make them? So there are two main techniques which we use. One is called as a molecular wave epitaxy, and otherwise another technique is called and metal organic chemical vapor deposition, or MOCVD. Molecular wave epitaxy is called MBE, and metal organic chemical deposition is called MOCVD. And then we use, in our lab, we use mainly MOCVD because that's what we've got in our lab. Also, MOCVD is widely used in industry. For example, today, if you are buying any LEDs or lasers, and most likely they have been made out of MOCVD because of the fact it's a scalable process. That means industry likes it. So there are two within the growth techniques, and there are two methods which we use. One is called as a metal catalyzed VLS growth process, vapor liquid solid growth mechanism, and another technique is called selective epitaxy. So in this case of metal catalyzed process, we take some gold nanoparticles, and then you can buy these days gold nanoparticles in a colloidal solution from 5 nanometers up to 300 nanometers or so. You take a droplet of this colloidal solution of gold, and then typically we use 30 or 50 nanometers, and we put a droplet of that solution on top of, say, for example, gallium arsenide substrate here. And then it turns out that the gold has got a melting temperature more than 1000 degrees Celsius. But once gold reacts with aluminum or gallium or indium, then the alloy, gold gallium or gold aluminum or gold indium alloy, its melting temperature is as small as 350 degrees Celsius or so. So now if you put these gold nanoparticles on top of gallium arsenide, gold is reacting with the gallium in the gallium arsenide. And then what happens is that you create this eutectic liquid, and then introduce the gases needed for the growth of gallium arsenide, for example, trimethyl gallium and arsine. And these gases get incorporated as liquid alloy. It gets supersaturated, crystals start precipitating out. It is like dissolving sugar in the water. You can dissolve sugar up to a certain point, and if you exceed the solubility limit, sugar crystals start precipitating out. The same physics is happening here as well. So gold particles are always sitting on the top, and then nanowire is below that particular gold nanoparticles or so. In fact, here is an example of a gallium arsenide nanowires. These were grown by Professor Hannah Joyce, who is now a full professor at Cambridge University in electrical engineering department. During her PhD at the AUNU about 15 years back or so, she has really demonstrated atomically perfect gallium arsenide nanowires, which are cylindrical in shape with no tapering or so, which was a major problem till that point. She developed a technique called two-temperature growth process, where we start the growth around 450 degrees Celsius and then reduce the growth temperature after a minute or so that you can suppress the tapering, which really has been a problem till that point. And as a bonus, we found that these nanowires are absolutely atomically perfect. And you can see the transverse electron microscope image of these particular gallium arsenide nanowires. And then this part is called a gallium arsenide. This is called a gold nanoparticle, which is sitting on the top, for example. So these nanowires are absolutely excellent materials for making quite a variety of devices, which I'll come back. But we made the nanowires as small as 10 nanometers in diameter, as big as 300 nanometers or so, using this particular technique. We've also demonstrated indium phosphide and then indium arsenide and a wide variety of 3,5 compound semiconductors. In the case of selective epitaxy, and in this case, we don't use any metals. Sometimes it's not convenient to use metals. For example, if I want to grow 3,5 nanowires on the silicon, and the gold is not a very good material for silicon, for example, gold acts like a non-radiative recombination center. So in this case, what we do is that we deposit some silicon dioxide by using plasma enhanced chemical vapor deposition, PECVD, and then deposit some ZEP photoresist, do electron beam lithography and create patterns of holes. And then you etch through those patterns of holes so that you can expose indium phosphide substrate in this case. Everywhere else is silicon dioxide is there, in the holes indium phosphide is there. Then you put this one to the MOCVD reactor, heat it up to somewhere between 650 to 750 degrees Celsius. Those are the typical temperatures which are used for growth of epitaxial layers, for example, in 3,5 semiconductors in MOCVD, and then introduce the gases needed for the growth of indium phosphide, and so in the trimethyl indium and phosphine. These gases dissociate, and then the nanowires start growing in the holes which we have created. Wherever there's silicon dioxide, no growth takes place if you choose the right conditions. This is a work of Dr. Chian Gao, who is now a research engineer in blue glass in a company in Sydney. And so during her PhD, she demonstrated these excellent indium phosphide nanowires, which are ordered patterns. You can see the top view. beautiful hexagonally faceted structures and ordered patterns because we created ordered patterns of holes, for example, here. We have taken these indium phosphide nanowires and then excited them with a laser pulse and look at the light emission, like a photoluminescence. So we quantify the quantum efficiency of the light emission as a function of the excitation power of the laser. So you can see that the red curve is for the indium phosphide nanowires, and which show quantum efficiencies as 50% or so. And then the blue curve is for epitaxial layers, or the two-dimensional layers. And then they also show very similar performance, indicating that despite large surface area of the indium phosphide nanowires, and really they don't really create any problems in terms of surface defects or anything, because generally when you got a surface, you always have broken bonds that leads to defect states, and that leads to in poor performance in terms of light emission. But in the case of indium phosphide, that's not a major problem. But whereas in the case of gallium arsenide, that's a major issue. You need to do some sort of a surface passivation by coating this with a layer of aluminum gallium arsenide or so that carriers cannot go to the surface. Otherwise, you don't see much emission of light in gallium arsenide. But whereas in the case of indium phosphide, you don't have to do that one. So we've also been working on gallium nitride material system. There's a work of Dr. Sonal Chandadikari, and so he came from C.D. Pilani, and then he did a PhD. He's now working as a postdoctoral fellow in our group. So during his PhD, he tried to grow the gallium arsenide nanowires first, and then coat this with the aluminum gallium arsenide, the so-called core shell structures, which I was mentioning to you. But in his PhD, what he has shown is, whenever you use a carrier gas, which typically use like a nitrogen-hydrogen combination in growth of gallium arsenide structures, epitaxial layers normally, and then there is surface etching takes place, and then you end up getting a lot of striations on the surface. But if you remove hydrogen and only use nitrogen as a carrier gas, you can get excellent smooth layers and atomically perfect layers also, which you here was able to show. And then you can see also the cathodoluminescence of these structures, and then with is a core here, and then the shell here, for example, here. And then he changed the composition of the aluminum gallium nitride shell from 15% aluminum, 30% aluminum, and 50% aluminum. So to be able to tune the band gap of the aluminum gallium nitride layer so that we can go to the ultraviolet region of the electromagnetic spectrum. Here is the cathodoluminescence again here from this particular structure. When you got this using nitrogen, hydrogen, light emission is not very good. But when you get rid of these striations and defects, and you get excellent light emission from these particular structures. So you can see that whenever you go and look at cathodoluminescence, because of the fact that we are going to larger photon wavelengths, and it becomes easier to be able to excite the electron hole pairs using electron beams in an electron microscope than a laser, for example, where we're able to show that you can tune the emission wavelength of this aluminum gallium nitride as and when you are really tuning the composition of the aluminum, and which we are going to is the ultraviolet region of the electromagnetic spectrum. But we also have been seeing an additional peak here, and then we wanted to figure out, is it due to the decomposition of this aluminum gallium nitride layer, or the segregation, or something else? It turns out that the work of Sonal Chandadikari has shown that these are related to the impurity-related defects. Because generally, whenever you grow the aluminum gallium nitride, aluminum likes oxygen. That means you end up creating this so-called group 3 vacancy, and oxygen on the nitrogen side defect complexes, they emit light in this particular wavelength region. So otherwise, these are excellent materials from that point. So now let me come back, and then this work of Dr. Naeem Wong. He is now a research engineer in Australian National Fabrication Facility at the ANU. During his PhD, again, he has done the same thing. Instead of opening a hole, what will happen if you open other slots, other features like slot or a ring, for example? He has taken indium phosphide substrate, deposited some silicon dioxide, did some ZEP or PMMA resist, did electron beam lithography. Instead of opening only holes, he has also started opening these slots and rings and etch through so that this indium phosphide is exposed in these regions, these blue regions, for example, here. He changes various growth parameters like temperature, 5:3 ratios, and total flows, pressures, and all these things. I'll not have time to go into the details of these ones, but I'll share with you the conclusions of his work. So here is the case when you open this slot along a particular crystallographic orientation of 101 bar, and then heats it up to 60 to 80 degrees Celsius and introduce the gases needed for the growth of indium phosphide. And what you end up getting is beautiful, these nanomembranes with these sidewall facets of 101 bar 0, for example. But you open the slot along another crystallographic orientation of 112 bar, and you do the same thing. And again, you get these membranes, but these membranes are a bit thicker than these ones because of the lateral groove taking place. And then the sidewalls now have got a 112 bar 0 crystallographic orientation. These are determined by the crystallography of the structures, which we're really growing here. But you open the slot in between these two orientations, you end up getting these beautiful diamond-like structures with these alternating sidewall facets of 101 bar 0 and 112 bar 0 or so. So what will happen if you open a ring? And again, Nayan Wong has shown that if you open a ring, you can get these beautiful ring-like structures with these alternating facets, which I've shown you earlier. Keep on growing further, and then you end up filling the gap here. You end up getting these horizontal membranes. And if you keep on growing further, you end up finishing off with these hexagonally faceted structures, because crystals always likes to be in the lowest energy facets also. Nayan Wong has taken these nanostructures of nanomembranes, nanodiamonds, and nanorings, and then did cathodoluminescence to look at the light emission. You can see the bright light emission from all these structures and very uniform light emission, indicating that the 4 years of hard work of Nayan Wong has paid off. These are excellent structures for making nanomembrane lasers or ring resonator lasers or for MEMS applications and a range of applications, for example, which I will come back to. So now you can see that we can make all sorts of exotic structures, and so you can see that you can make even gear-like structures, and so the spiral-like structures, and then ring-like structures, and a range of things. And depending on what star-like structures, depending on what applications you have, you end up choosing a right kind of structures, for example. In nanotechnology, we focused quite a lot on in terms of what is the impact of the size of the nanostructures on the electronic and optical properties. For example, nanocrystals or nanowires and how they changes the light emission characteristics, for example. But we have not spent huge amounts of time in terms of understanding the effect of shape on the electronic and optical properties, and that's what we're exploring at this stage. So now let me move towards the devices now, because till now I've shown you mainly the materials and then how to grow these nanostructures of nanowires or nanomembranes or nanorings or nanodiamonds. But now let me really use those ones to show you wide variety of optoelectronic and sensor devices and energy devices as well. So we have been working in the area of nanolasers for more than a decade or so. And many students have worked on a wide variety of lasers, and I lack of time to go into the details of all of them. And I'll share with you some of the lasers which have been demonstrated by Dr. Drew Saxena, who is at Imperial College now. And so then again, Dr. Chian Gao has demonstrated indium phosphide lasers. And then Dr. Tim Burgess has demonstrated zinc-doped gallium arsenide nanowire lasers also. This work has been led by my academic colleagues, those have been listed here. So if you take, just to jump from that 10 years back to today, what we're doing is that we are taking these nanowires and transfer them onto a glass slide so that you capture a good, so that you can see, you look at this nanowire acts like a waveguide. So because of the fact that these nanowires have got a high refractive index, and then the air has got a refractive index of 1, and these nanowires have a typically refractive index of 3.4. So that means both ends of the nanowire acts like mirrors, and so they essentially each nanowire act like a laser cavity. You don't have to create any mirrors or anything of that sort. Naturally, these nanowires form into laser cavities. So in this case, what we are showing is that these materials like gallium arsenide or aluminum arsenide and various materials, they got nonlinear optical properties because of lack of centrosymmetry. So what happens is that, if you really, nonlinearities lead to second harmonic generation or so. That's what I'm trying to show you here. So you take this nanowire of this particular structure, and particularly what we have done is that we've grown some indium gallium arsenide quantum disks within the gallium arsenide nanowire, transfer them into a glass slide, excited them with laser pulse, and look at the light emission. So the primary light emission, the fundamental mode, is emitting at 1060 nanometers. You expect it to have a second harmonic generation. Second harmonic, you expect it to have at the shorter wavelength of the twice that of the half of the wavelength, or the twice the frequency. and you end up getting the light emission at 508 nanometers because of the fact that this is because of the so-called Chi2 nonlinearities, and which leads to these particular properties. Now you can see, using the same nanowire, I can make a near infrared light emission as well as a visible light emission of the green light here as well. So that means you can use it for a multi-wavelength lasers, which are needed for digital printing applications and a range of things. But typically, you don't expect it to have, this is a normalized plot here. And then typically what you would end up having is that, primary fundamental mode has got a much higher intensity than the second order mode. And here I'm plotting the fundamental mode intensity versus the second order mode. And you can see that this log-log plot shows the slope of 2, indicating that these are the so-called Chi2 nonlinearities, for example. And again, this work has been published in 2022 or so. This is a work of Fan Lu Zhang and Shotao Gan and Shotao Zhang and EE and various colleagues here. If you increase the diameter of the nanowire, what happens is that you can really sustain multiple modes. That means you can see that the multi-frequency lasers and emitting different wavelengths of color here, for example, the fundamental mode. And then you can see also, not only you can create the second harmonic, you can also create the sum and then difference frequency of these harmonics as well. So here's a case we're able to show that the second harmonic of the twice that of the omega 2, and then we're also showing the omega 2 plus omega 4, and then also you can see omega 1 and omega 2, and the 2 omega 1 and the range of frequencies. Now you can see, using the same nanowires, you can create a multi-wavelength lasers, essentially changing the diameter of these particular nanowires, and both in the near infrared region of the spectrum, as well as in the visible region of the spectrum as well. Particularly these sorts of lasers are important for sensing applications and a range of things. Now let me move to another kind of lasers. And in this case, what we wanted to create is so-called vector beam lasers. So in this case, again, we created the so-called indium gallium arsenide quantum dots within the nanowire. You can see the beautiful, these EDS patterns of these indium signals here, for example, showing these beautiful indium gallium arsenide quantum dots within the gallium arsenide nanowire here, for example. So in this case, what we're doing is that we're designing these cavities such that, and so you end up having only the reflectivity is coming in the region where it is in the circular form here, for example, only in the shell part, because in the core part, there's no refractive index difference. And because these nanowires grow outside this hole here, for example, because of the lateral growth, and then in this ring-like structure is the one where you got SiO2 here, that means it creates a resonant cavity here for the ring-like structures here. So that's how we want to create these so-called vector beam lasers. So you can see that, to cut the long story short, and then we have taken the images of these vector beam lasers, and then by rotating the polarization of these structures, we're able to show that you can get these azimuthally polarized vector beam lasers. That means essentially they're looking like a donut-shaped lasers. That means they can be very useful for making the trapping of the nanoparticles, the trapping of atoms, and a range of applications, and which we're exploring in this particular case. And again, this work has only been published last year or so. Again, Professor Shotao Gan's lab, which we collaborated with, Shotao Zhang, and many students are involved in this particular work. So now we asked ourselves, what about ring resonators, which I was mentioning to you? We're able to grow these ring resonators. In fact, these microcavity lasers have been around for quite some time. And because they can be, so we create something called a whispering gallery mode lasers, for example. If you want to couple this light into this one, because it's circulating in this ring like this, you put a waveguide next to it, light leaks out, and then you can couple to the optical circuits here, for example. And we've gone off and then again designed these structures, and then we do a lot of simulations to be able to design the right kind of dimensions. For example, what should be the width, the diameter of this ring, and then what should the width of the ring, or what should the height of the ring, or so. This is the work of Dr. Wei Wang, who during his PhD, he has demonstrated these lasers, who is now a postdoc in the group. You can see that based on his design, and he's gone off and grown these structures, and then excited with the laser pulse and look at the light emission. See, below laser threshold, and you see a broad light emission like an LED, above laser threshold, and you end up getting these beautiful whispering gallery modes, as you expected theoretically, which is shown here. We use something called FGD simulations, finite difference time domain simulations. And again, a broad light emission like an LED below threshold, and a narrow light emission like a laser, for example, above threshold. And you can also see the threshold-like behavior here. and then the log-log plot showing the S-type behavior. That's what we'd expect. These are the first indium phosphide bottom-up approach grown ring resonator lasers. And because we are going from the bottom up, there's no damage has been created, which typically is an issue when you're doing the top-down plasma etching process. Plasma etching leads to damage, for example. Then we asked ourselves, what will happen if I bring the nanowires and nanorings together? Again, this is a work of Dr. Wei Wong with Dr. Nain Wong, and my colleague, of course, Professor Ho Tan, is leading this particular project as well. So we asked ourselves, can we really grow a nanowire along with the nanoring in a particular structure, for example? And we have done simulations, and then simulations show that if you grow these structures, the light gets coupled into the nanowire, and you expect it to have the vertically emitting nanowire laser, for example, along with the ring here, for example. I told you in the case of ring resonators, only whispering gallery modes, instead of putting a waveguide next to it, and we wanted to essentially nanowire acting like a waveguide or an antenna, for example. So again, we've really made two types of structures, and then the ring is here, the nanowire is a bit far away from the ring, and in this case, the nanowire is closer to the ring, which we call it a strong coupling. Again, a lot of simulations and hard work took place in terms of growing the structures and characterizing them. So you can see that when you have got the system A, the weak coupling, for example, ring only, the light is circulating here, but you expected to have, is it the ring plus nanowire, light is expected to come from the top, and that's what we are seeing experimentally here. And then the polar plot shows also that if you do not have, you only have the ring, and then you can see that this polar plot shows like this. And in the case of the coupled structure of the ring and nanowire, light is emitting vertically. And of course, again, if you use this strong coupling, again, in the coupling will be quite different. And again, vertical emission is taking place, but the shape of this profile is slightly different. And again, the simulations and experiments were able to match very well. And so that means for the first time, we're able to make these vertically emitting micro ring nanowire lasers, for example, which are important for example, developing the so-called holograms coming out of your phones in the future, for example. So till now, I've only shown you optically pumped lasers, but ultimately we want to be able to make electrically pumped lasers, and this work of Dr. In-Suk Yang, and then he came from Samsung, he finished his PhD, and now he is working for Facebook, for example. So during his PhD, and so he made this P-type indium phosphide, and he made this green one here, and then he's coated with indium gallium arsenide yellow layers here, and then he finished off with the N-type indium phosphide with another type of dopant, like a silicon doping here, zinc doping here, for example. Again, he spent more than 2 years to optimize these structures so that he can get a good quality structures here, for example. And then he transfer them onto a glass slide, and then make contacts using electron magnetography so that you can inject current into these devices and then be able to see. And he's able to really successfully make these PN junctions, which I was talking about earlier. This work is led by my colleague who is listed here, Professor Lan Fu. So you can see that the IV characteristics show like a nice diode-like behavior, indicating that the hard work of In-Suk has paid off. And then we've gone and looked at the light emission from these structures. As and when you're increasing the amount of current you're injecting into this particular device, and higher the amount of light coming out of these structures. And you also see two emission peaks because the quantum well, which is on the top, has got a different composition thickness than the quantum well, which is on the side walls. And that's why you end up having two different emission peaks here, for example. But if you plot the output versus current, you do not see any threshold-like behavior. It's only increasing gradually. That means they are acting like an LEDs, not like lasers, for example. So the question now comes, you got a PN junction, you got a laser cavity. What's the problem? Why you're not able to make nanowire lasers which are electrically injected? It turns out whenever you put metals to inject current, also metals have got optical losses in this wavelength region, for example. So that means you're creating a lossy cavity. You need to pump it harder to get over the losses. You're creating heat. Heat reduces the gain. It becomes like a vicious circle. So then, in fact, before In-Suk finishing off, he's also demonstrated a multi-nanowire LEDs. And again, you grow these nanowires, which I've shown you earlier. And then to make contacts on the top, you fill this with a polymer and then etch selective the polymer, expose the tips of the nanowires, and we coat with indium tin oxide and put some metal contact at the top and the bottom, for example. So again, look at the IV characteristics showing like a diode-like behavior. You inject more and more current and you get the much higher light emission, for example, here. And still again, it's not narrowing the line width. That means it's not acting like a laser. It's only acting like LED. In fact, below this probe, you can see a bright light coming out of these ones. But because now we are embedding these nanowires into polymer, you can peel these things off and you can make this so-called flexible LEDs, which Samsung and Apple and others are interested for flexible phones and flexible computers and others. So another student came, Dr. Nikita Gagrani, who came from IIT Kharagpur, and then she looked at this one, how to replace these metals and with some transparent conducting oxides, aluminum doped zinc oxide, indium tin oxide, and again p-type oxides like the copper doped tin oxide and various things, for example. So Nikita Gagrani, despite all her efforts, it turned out that though even after removal of these metals, and still the heat generation has been a major issue, and we are not able to demonstrate electrically injected nanowire lasers. And based on her, now Dr. Nikita Gagrani is working at LAM Research in California. And then based on her work, now we are redesigning new class of lasers to see how we can be able to achieve these electrically injected nanowire lasers. So now let me move towards
Sorry
other
to
devices.
interrupt you, sir.
Sorry?
We have 10 minutes left for the talk.
Okay, thank you. So now we are also looking at terahertz detectors, and again, terahertz radiation is important for in terms of the security purposes, because they can detect the metals, for example, in the airports and other things. Again, we're using nanowires, and then you make some contacts again. This is work of the Kunpang, who is now at postdoctoral for Dr. Kunpang, who is at a postdoctoral fellow at Oxford University. There's a joint work with Oxford University. Again, during her PhD, she is able to demonstrate that we can make use of these nanowires and be able to make excellent performance nanowire detectors, which are much more compact than the bulk reference detectors typically currently used in industry. And so really, she has demonstrated a broadband detectors, which are shown here, simulation show here, and then her measured nanowire detectors and bulk reference showing that they're very much similar, despite the fact that they're much smaller than the bulk detectors, for example. During her postdoc, she has also demonstrated polarization resolved terahertz detectors by putting two sets of nanowires 1 to 90 degrees to each other. So in the process, what you could do is that you can be able to really make the so-called polarization resolved terahertz detectors. And again, I probably will not have time. The key message is that simulations of what you would expect from the terahertz radiation, which is passing through a terahertz metamaterial, and X and Y polarizations, which you would expect for transmission of light through these structures. Our simulations and experiments are matching very well. And she published this work 3 years back also in Science, for example. Now let me move towards solar cells. And again, nanowires have unique opportunities to be able to make use of them for solar cell applications. And one of the unique things is that you can be able to make the nanowires as long as you want to absorb the sunlight and make PN junctions, which are like a core cell structures. So that means you'll be able to make this so-called core. That means you'll be able to collect the carriers very efficiently, for example. Also, the nanowires act like light funnels, and also they got low reflectional losses as well. So that means nanowires are very attractive from the point of view. Again, we do a lot of simulations to identify what should be the height of the nanowire, what should be the diameter of the nanowire, what should be the diameter to pitch ratio. And then there's the work of Dr. Vidaraj, who is a postdoctoral fellow in Glasgow University. And now, in fact, he's returning back to India to National Physical Laboratories as a Ramanujam fellow also. So what he has done is that he's taken these p-type indium phosphide nanowires and coated with the atomic layer deposition of n-type zinc oxide and aluminum zinc oxide, so that he is able to create these so-called core shell nanowires. And then by doing this one, he is able to demonstrate we can get solar cells, which are about 17% efficient, which looks very attractive. Also, we embed these nanowires also again with a polymer to be able to make contacts. That means you can peel these things off. So that means you can make flexible solar cells, which we could be able to, in the future, have these things on backpacks so that you can charge your electronic devices, for example. It turned out that these same solar cells turned out to be very good for detection of these single photon detectors. Single photon detection is important for quantum communications. And again, Dr. Vidar Raj and Dr. E. Zhu, both the postdocs worked together and they were able to demonstrate the single photon level detection using these solar cell detectors, for example. Again, we're using nanowires for splitting of water to generate hydrogen as a clean energy source. And as you know that while the solar cells are very good, but at nighttime you don't have solar energy, that means you need to have storable energy. Either you can use batteries, or otherwise you can also create hydrogen as a transportable and a clean energy source. We take some semiconductors and then we shine light on them. Electron hole pairs are generated. holes go and then essentially split water to generate protons, and electrons come here, then they meet with the protons here, they create hydrogen here at the cathode area, for example, here. We've taken gallium nitride, and then again, we're able to show that normally the major challenge is that either some materials are, electrodes are efficient but not stable, but some materials are stable but not efficient. Gallium nitride is typically difficult to etch, and we wanted to look at whether gallium nitride, how the nanorods of gallium nitride behave like, and then it turned out even gallium nitride, which is normally very stable, under these photocatalysis conditions are not that stable. We had to coat it with the cobalt oxide so that they act like a co-catalyst and also acts like a passivation layer, and there we're able to show that you can get stable structures here. And again, gallium nitride is not the ideal material. We're exploring other materials as well. Again, of course, I know that I'm running out of time, and we are using nanowires for detectors. And in this case, we're able to show this work of CU Wei, my student, and we're able to show that you can use these indium phosphide nanowires for nitrogen dioxide detection, which is a major pollutant which comes from the cars and other things. That means, in fact, many people die because of these pollution effects. And we're able to use these ones, particularly take these indium phosphide nanowires, only coat only part of the nanowire so that you can really have to make contacts and expose the nanowire to the gas, and we're able to show that you can get to selective and highly sensitive nanowire sensors here, for example, nitrogen dioxide sensors. If you create a PN junction within the nanowire, we can also create these so-called cell-powered nanowire nitrogen dioxide sensors, which are important for Internet of Things and a range of applications, for example. Just the light in the room is sufficient to be able to provide enough energy to the sensor, and it's a self-powered sensor, for example. And most recently, we have taken these structures to be able to analyze acetone from the breath, because the people with diabetes, and then they bring out acetone in the breath, and by measuring that one, we're able to show that you can really be able to detect as small as 0.4 parts per billion, and also as high as 1,000 parts per billion or so, and thereby be able to detect people without having to do the pen pricking or anything. And things like ketosis. Ketosis is a major problem for diabetics, and in fact, we developed something called a keto vessel. And this particular keto vessel recently won an award from the Australian Diabetics Innovation Challenge. And my colleagues have really developed this particular work, for example. And this is a work of Professor Vinay Gautam, who is now at SENS in IEEE Bangalore. She spent some time in our group. And again, these nanowires are used for growing neuronal circuits. And we take neurons, and then we really look at how these neurons are growing on top of these indium phosphide nanowires. You can see the neurites really follow these patterns of these nanowires very beautifully here. You can see the dendrites which are coming out of this one here as well. So if you got these nanowires in this case here, then you got more than one neuron, they really form into this neuronal network. In this dash box is the one where you got lots of neurons, and you can see that these neurites are really following these patterns. Axons and all follow these patterns. Outside these nanowires, they really make random connections or so. Dr. Gautam has done something called calcium imaging to look at how these neurons are firing, for example, and how the signals have been, the action potentials have been fired. And then where she does something called calcium imaging and take a video and then see if neuron is firing, what's happening to this neuron and this neuron, these astrocytes, and creates correlation maps. And she has shown that when you grow these neurons on glass substrates, change in fluorescence as a function of time, and there's very little correlation, but whereas if neurons grown on indium phosphide nanowires, there's an excellent correlation is taking place, indicating there's some sort of a synchronized and correlated activity is taking place. 5 years back, when she presented this work at a Melbourne neuroscience conference, they asked her what neurons you're using. She said she's using mice neurons. They said, how about you using human stem cells? So now we are working on taking the stem cells from the Alzheimer's patients and then the stem cells from the healthy people, and using CRISPR-Cas9 technology create the brain organoids, and then be able to really use these organoids to be able to see the signaling differences between the Alzheimer's patients and healthy people, so that we can be able to differentiate those signals so that we better understand dementia. Also, we're using nanoelectrodes to be able to measure the signals as well. And really, it's an exciting project of involving stem cell biologists, neurobiologists, computer scientists. We are applying artificial intelligence techniques as well, so that you can be able to help people with the dementia in the longer term. With that, in conclusion, nanowires open up opportunities for manipulation of light matter interaction at the nanoscale, on developing new class of lasers, LEDs, infrared and terahertz detectors, solar cells, PC water splitting, and sensors and engineering the growth of neuronal networks. Let me finish off with some information. And I'm currently serving as the editor-in-chief of the Applied Physics Reviews. And so it's a high impact, it publishes high impact original research articles and reviews. You got some breakthrough results or anything, and then please keep the journal in mind. And once in a while, we advertise positions for PhD students and postdocs in our Center of Excellence. Please keep an eye on this website. Since I started my life in a small village in India, and I benefit from generosity of my teachers and many people, and as a gratitude to them, my wife Vidya and I've started an endowment to support students and young scientists coming from the developing countries. And based on the success of this particular program, our university started the Future Research Talent Program with India and Indonesia, and many students came from IITs and ICES and various places. And in fact, last year we had about 92 students, and 75 of them came from India and 17 came from Indonesia, and including 4 scholars from our Jagdish endowment. And then this is those group of people, bright young people working in astronomy, biology, chemistry, physics, engineering, computer science, and science communications, and medical sciences, and earth sciences, a range of things also. With that, I'll stop here and happy to answer any questions you may have.
Thank you so much, sir, for this talk. I would request participants to ask their queries, and you can switch on your video, unmute yourself, and can ask the question. You can even post your questions in the chat box.
Professor Lanja, I think he was raising his hand. Sir, kindly unmute and you can converse.
No, I think he was only clapping if I can see, but he can ask me questions. I'm happy to answer for sure.
Okay, hello. Thank you very much for the amazing presentation. I really enjoy it, especially the final part with the neurons. And this looks like a little bit like science fiction, but you are doing big progress on this. I'm very interested. Um, I have seen recently also one talk in this direction from a scientist in Harvard, a Korean scientist, and it is very interesting. I would like to ask one quick question, which is I saw one picture in which you have the neurons and then you have one array of wires. And then I guess in the center, in this crossbar region, is where you put the neurons and then you measure these electrical signals. I would like to ask um, if there is any special requirement in terms of materials for this sample. I mean, in terms of substrate and metals, or which kind of materials do you use, or if it is not confidential, of course.
No, it's not confidential because I do science for fun. You know, so I share everything what I do. We don't try to keep anything confidential because science should be beneficial to the humanity and so on the planet. And so basically, we have to use biocompatible materials. Mario, that we started off with the gallium arsenide nanowires, but unfortunately, the gallium arsenide nanowires is not a very good material because the neurons start dying because it's not a biocompatible material. It turned out that indium phosphide is a very good material and it's a biocompatible material. We looked at silicon. Silicon is also a very good biocompatible material. Platinum is we also looked at platinum nanowires, for example. Again, platinum is also biocompatible. We have to choose materials which are biocompatible. If they're not biocompatible, these neurons are not going to survive. And that's why we have confined ourselves to indium phosphide. But another reason also, you can shine light and be able to excite the photocarriers in that one. So that means you can also do the optogenetics and a range of things. And that's why we have chosen indium phosphide being a direct band gap semiconductor as well. So that's one of the reasons that we've gone for indium phosphide. But it turned out indium phosphide is very good. And even people have shown gallium phosphide works as well. And in addition to using these neurons for neuron growth and other things, in fact, I spent in 2018 5 months in University of California, San Diego, Professor Shadi Daye's group, and Shadi Daye has been really using these nanowires for measurement purposes. And in fact, I've seen some beautiful videos, and these neuroelectrodes have been used to really measure signals from the people with things like the so-called some of the neurological disorders like epilepsy, and then be able to identify which part of the brain is not really providing the signals, and then be able to, neurosurgeons are able to only do the surgery just in the regions where they're able to measure and then identify which part we should really remove. Earlier, they used to really follow based on their knowledge of the brain and on which part of the brain really triggers these problems of the epileptic fits and things like that. But now these measurements are enabling you to be able to do that one. You can use the nanowires for both measurement of the signals as well as engineering the neurons as well. So we're exploring both of them.
I see. Thank you
Which is
very much. Thank you.
Thank you. That's a minute. So this is really very interesting, basically the interesting area, but also I'm learning a lot because I'm not a neuroscientist, working in a multidisciplinary fields is really great fun.
Yeah. Thank you.
Thank you.
Participants, any other question? You can even write in the chat box also.
Don't feel shy, guys.
So, sir, I have a question.
Sure.
You have shown various complex nanomaterials. So they have like a star shaped and other shape. So I want to inquire like how different is the property of that individual, say, star shape compared to if we place the basic buildings like suppose say one material is a V shape and how different would be its property compared to two slabs which are comprising
Sure.
the pieces.
Okay, that's a good question. Again, you can be able to change the polarization properties of these structures will be quite different. So that's what we are really exploring, and how the shapes are influencing. Of course, what happens is also the shape also influences the type of facets you have got. Those different facets also have got different surface properties as well, which could be used for sensor applications and also electronic applications, and as well as also for controlling the light polarization properties as well. So that's why these changing the shape really opens up lots of opportunities. Again, we are exploring these membranes for MEMS applications and a range of things as well.
Okay, sir. And sir, one more question I have is that I'm not from optoelectronics domain, but I would like to know that how means there are transistors which are being made where the gate terminal instead of gate there is a optical part which is switching on and off the transistor. So if you have an expertise in that, can you comment how a large scale integration of such transistor will be can be made?
It's very interesting you asked that question. In fact, it turns out that the indium gallium arsenide nanowires have been used. Interestingly, when you make transistors, most of the time we are doing the horizontal connections, right? But whereas in the case of nanowires, you can make the vertical connections. So that means you can be able to put much more high density nanowires. And in fact, the IBM Zurich's group and Heike Riel's group has demonstrated these indium gallium arsenide nanowire transistors on 6-inch silicon wafers. So indicating that it is possible to be able to large scale areas. And of course, you need to do the patterning. And of course, you're not going to do electron beam lithography patterning at that level because of the fact that it will take forever. But you can do the nano imprinting and techniques which people have developed. Initially, use electron beam lithography to identify the structures which I would like to get. And once you identify the design which you want to have, and then you can be able to go to the nano imprint and various imprinting technologies to be able to make large scale areas as well.
Thank you, sir. That was a very interesting perspective. And sir, before I pass on to our anchor Shruti, I would like to convey regards from Professor Saibal. He had a meeting, so he had to depart early. So he conveys his regards.
Which is fine, no problem at all. And then I think somebody asked me about 2D materials. Yes, 2D materials are emerging materials, and there's a lot of potential out there. And people have already been demonstrating, including, in fact, my colleague with Uri Lewis group, and we demonstrated in an atomic layer optical lenses and for light focusing effects and range of things. And there's a lot of potential out there, particularly for making flexible optoelectronic devices, for example, because of their flexibility. And in fact, we are using these 2D materials and growing the nanowires, for example, on hexagonal boron nitride, growth of aluminum gallium nitride nanowires, and also growing nanowires of gallium arsenide and mica, which is also a 2D material. And it's really, there's lots of potential out there, but there's a lot of work need to be done still.
Yes, sir, you have, I think you have answered Souvik Mandal's question.
Okay, thank you,
So,
Shruti.
any other queries from the participant side?
They want to go and get their lunch or coffee or whatever is available out there.
No,
Hello, sir.
Yeah,
I
go
have a
ahead.
question that how does the choice of a catalyst in VLS growth impact the morphological properties of nanorods?
Okay, that's a very good question as well. So basically, you have to choose the right kind of catalyst, and it doesn't have to be gold. And in fact, we have shown that you can use palladium and platinum and silver as well. So key thing is that you need to have a catalyst which can react with one of the elements of the material which you're depositing, and it need to have a low alloy need to have a low melting temperature. So that's a key requirement which you need to have. Once if you do that one, you can be able to really make use of any catalyst which you would like to have. So again, the shape is very much also again dependent on how you are really optimizing the growth conditions. By the way, all the results which I've shown you is a lot of work by students or postdocs. Sometimes each slide may have 18 months or 2 years, sometimes 3 years of hard work, be able to get those beautiful results. And those of you, those are students or postdocs or so, keep working and don't get the results day one. And you don't in research, it doesn't happen that way. Your persistence and perseverance lead to the great outcomes which you're hoping for.
Okay, sir. Thank you, sir.
Thank you.
There is one question in the chat box. What about the stability for the 2D material application?
So it depends on what you're doing. For example, we have been working on hexagonal boron nitride. Hexagonal boron nitride is a very good material, and it's a very stable material. And also being an insulator, in fact, hexagonal boron nitride is used, for example, to be able to isolate the materials like molybdenum disulfide or tungsten disulfide or so, and so that they're not interacting with the substrate, for example. Of course, depends on what material you're looking at, and depending on what material you're dealing with, we need to look at the stability aspects as well. For example, typically you don't really operate three-phase semiconductor nanowires devices more than 300 degrees Celsius or so, because arsenic or phosphor may start leaving. So depending on what applications you have, but most of the time at room temperature it's not a problem, because if you're using an LED or a laser, and they're all you're operating them, they're all made out of three-phase semiconductors, for example, including a lot of detectors also. If you go to very high temperatures, of course, gallium nitride materials are better, silicon carbide is better, and depending on what applications you have to choose the right kind of material.
Very good
I
afternoon.
think
Shruti, may I
you
ask
can
one
proceed.
question?
Yes, you can proceed.
Very good afternoon, sir. Myself,
Good
Chandwan Patel.
afternoon to you, Chandru.
Yes, sir. Sir, my query is that actually, as the graphene invention has started in 2004, so I think it was much more popular at that time. The growth of 2D materials after graphene invention. But after certain years, as the academic research progress, it is found that that material actually is not suitable for practical application due to the band gap limitation and other actually restriction or limitation with the graphene. Now, actually, the other 2D material has explored. Other families of 2D material, TMDs family, M16 families, and other families are actually getting much more popularity. So, what is your take on that? These material will also actually face this type of challenges in the coming years as it will progress, or it will actually sustain the in a practical application, because now humidity and other things are these materials, as actually you have mentioned in your last point, stability, regarding the stability.
Yeah, I think that's a good point. And of course, what graphene has done is that it opened the minds of the people in terms of what is possible in terms of developing these 2D materials. Okay. And again, graphene is used for some applications, but of course, as you identified, that some of the limitations it does got a zero band gap. So that means, so it's got certain limitations, but sometimes graphene is also used for some display applications, for example, as a contact layers and other things as well. So that is the beauty of, if you develop a new material, it makes people to think about other new materials which you can really develop. And I think, it depends on what you're using those materials for. You cannot blindly say that, one material can do everything. Typically what happens is that, Chandraban, that, for example, when we started about 25 years back, nanotechnology is going to solve all the problems of the world, but now you identified which ones nanotechnology is useful. For example, today, if you're using any electronic devices, they're all made out of 5 nanometer or 7 nanometer node, or we are moving towards 2 nanometers and all these things. So it means essentially you can claim that every electronic device which you're using is nanotechnology, for example. Again, nanotechnology, again, you need to think about, where these nanostructures or otherwise 2D materials can provide something unique with respect to what is already existing. If I say that I'm improving something by 10% or 15%, nobody is going to care about you. If I say that I can be able to change this one by order of magnitude, 2 orders of magnitude improvement, then people take these things seriously. Again, he's talking about perovskite solar cells, for example. In the beginning, we started telling about, the stability issue is a major problem, and of course, the humidity is a major issue, and all these things. And people are developing, coating these things with, the humidity barriers and other things, and able to protect these layers and other things. People are making improvement. Basically, human ingenuity is very high. And if you really give a problem, and then a large enough number of people are working in a problem, and they'll be able to find solutions, or otherwise, if you find a material, they can find an application for something which is useful for. But you cannot say that every material can be useful for everything. That's why the smartness comes what applications you're using and where it can really do a better job. For example, why 3-5 semiconductors are there with respect to when silicon is already there. The reason is that silicon is an indirect band gap semiconductor. It cannot emit light efficiently. So that's where you need to make lasers or LEDs. You need to have direct band gap semiconductors. That's why 3-5 semiconductors. For example, if today I'm able to talk to you because of internet is dependent on the lasers and detectors made of the 3-5 semiconductors, particularly indium phosphide material system, for example. Okay? Again, high-speed electronics. Again, if you're using cell phones and other things, they are made out of gallium arsenide, power amplifiers and a range of devices, for example. Depends on what you're doing. Gallium nitride power electronics has been used now, for example. Silicon carbide is used for power switches, for example. You have to choose the application and what material is ideal for the particular applications, rather than blindly claiming that, well, this can do everything under the sun. Of course, people create a little bit of hype initially, but that's something which you need to accept that as well. And when hype creators come and then go, but serious people will stay back and really do the good stuff.
Yes, yes. I completely agree with your point, sir. Thank you very much.
Thank you.
For an answer.
I think Shruti is very keen to close the meeting. I think I can see that she's getting anxious. Go ahead, Shruti.
No, sir. This was a very informative talk, and I hope everyone has enjoyed it. So I just request all participants to switch on your videos to just click a screenshot. Okay, so thank you so much. Just a minute. Okay. So I would like to thank to our distinguished speaker, Professor Chenupati Jagdish, President of Australian Academy of Science, the Australian National University, Australia. Uh, Thank you, Professor Jagdish, for an enlightening session. We are grateful for the time and effort you took to share your experience with our IEEE chapter. So, thank you so much, sir, for being here.
Okay, so thanks, Shruti, and good luck to all of you. And then I started the Australian chapter of IEEE Photonics Society and Electron Devices Society about 30 years back, and then that's how I became the president of those two societies. So that's my encouragement is that keep doing good work, and then there's a bright future ahead of all of you. Thank you very much.
Thank you so much, sir. No problem.